So for people watching this recorded, I forgot to mention to start the recording. So I'll speed through the opening slide. My name is Ollie, based at Queen Mary University of London, and this is my latest work, all to do with how we can visualize the outputs of generative systems. I've already said my thanks, so I'll get straight into it. So as I was saying, the motivation for this work is the techniques and process of visualizing the every possible output from a generative system so that they can be kind of usefully compared to alternative systems. This is a sort of important question for us as researchers. If we're looking to sort of claim that a novel approach is an improvement over a prior one, you know, for example, in terms of like the diversity it can produce, you need to have this kind of like high level view of, you know, every possible artifact. You can't just understand that from looking at individual artifacts. And it's also an important question for game designers. You know, if you're trying to tune your generator or pick the right generator for your given game, it's a very important question to understand like what total artifacts are possible. A couple of key terms that I'll be using over and over again. Generative space I've already mentioned, but the idea of a behavioural characteristic. These are often also called like metrics in the literature more generically. But by this, I just mean any like quantifiable characteristic of a piece of game content. You know, it could be a sort of heuristic for difficulty, some kind of a measure of some kind of aesthetic quality, and these could be extracted directly from the representation itself, or you could extract these from simulated play from an agent, say. Moving on now to sort of the key related work that inspired this particular project, primarily embeddings visualizations, embeddings extracted from neural networks, but also expressive range analysis. So when it comes to visualizing the outputs, well, when it comes to understanding the outputs of a generative system, a very common approach in FIRE PCG research has been to try and visualize the output space, most commonly using this technique called expressive range analysis that I bet many of you are familiar with. Part of ERA's popularity is very much related to how easy to understand it is and how easy to use it is. So to conduct ERA, you generate a sample of normally levels, but it could be other artifacts as well. Let's say levels. Generate a set of levels from a system, and then you calculate two or more behavioral characteristics of these levels, and then you can just visualize that set of levels, most commonly on like a 2D heat map, as we can see on the right hand of my screen there. And this is useful for both qualitatively understanding a generator in terms of like the likely artifacts produced, what kind of artifacts it struggles to produce, but also can be used in a more quantitative way as well to, you know, have a heuristic for the diversity of output or how much of the search space you're exploring. But ERA is not without its weaknesses. Most importantly for this work, you are typically limited to two characteristics at once. There are more niche techniques for visualizing multiple at once, but they have their own downsides, and you tend to be limited to two characteristics at once. So that means there's kind of types of diversity you can't see at the same time. You also have to recalculate these characteristics anytime you want to conduct ERA. So if you generate a new set of levels, you need to recalculate these characteristics, and that can be quite time consuming. And this brings us over to the kind of other main strand of related work, which is this field of embeddings visualization. Specifically, we were highly inspired by this paper, which actually comes from outside of games research. It's this principal paths paper from Gardini and her colleagues from last year, where they were using a technique that we'll be talking about in the following slides to produce 2D visualizations of like sets of artworks and music, but artworks are the most interesting for us. And similar to ERA, the goal for these kind of visualizations is that like levels or artifacts that are close together are similar in ways that we would recognize, which potentially, well, basically this paper was exploring, can we use this technique to produce ERA style visualizations of generative spaces without some of the downsides of ERA? So that moves me on to the approach that we used, which again is very similar to the approach used by Gardini and her colleagues in the paper I was talking about. There's three kind of high-level stages to the approach we looked at. All of the actual visualization generation happens in stage 1 and 2. Stage 3 is just related to evaluating these visualizations in a way that I'll talk about. So firstly, with stage 1, this is the process of training a neural network, specifically a convolutional neural network, or CNN, to be able to predict the characteristics of levels based on their encoded structure. So we first convert the levels to a one-hot encoded form, because we're looking at 2D tile-based game levels like Mario and other sort of like more old school tile-based games like that. So you can convert these to like a one-hot encoded form where like it's specifying what tile appears at each location in the level. And this is a nice machine readable form, which is great for sort of neural network training. And it's been done a bunch in like PCG machine learning literature. Once you've trained that network, this moves on to stage 2. We can create a copy of that network, and then with the levels we want to visualize, we do the same process, and we use the network to predict the behavioral characteristics. But right before the network is about to make the prediction, we basically discard that prediction because we're not interested in that for now, and we extract the embedding, which is the kind of the like from the penultimate layer of the neural network. This embedding is basically like a large one-dimensional vector of numbers, which is typically only sort of machine understandable. It's not meaningful on its own to us. But if the training has worked well, there's a kind of high degree of locality there, where basically similar vectors in this embedding space, and each embedding representing a level, similar embeddings indicate levels with similar characteristics if everything's gone to plan. And we can then extract those embeddings, apply dimensionality reduction techniques. We use principal component analysis in this paper, which is like an old school dimensionality reduction technique, to compress this large set of variables down to just 2, which explain as much of the variance in the sort of underlying embeddings as possible. And we can then visualize that. We can then visualize that into some simple 2D scatter plot, where each point is a level. So we've got these scatter plots now, but how do we know that there's actually useful information there? Well, this is where step 3 comes in, where we're interested in if there is basically correlation between the behavioral characteristic values and the distance between levels. The idea being, if you're finding good correlation, that means levels with similar characteristics are close together, and you're basically kind of getting expressive range analysis without some of the intermediary steps. And so to evaluate the extent to which is the case, we take every pair of levels in the visualization, calculate the Euclidean distance between them, and then look at the correlation between those values and the values for their behavioral characteristics. So that's basically the technique. Now moving on to the pilot experiments that we ran to explore this approach. So we looked at two games for these experiments. Primarily because there are these lovely open source level corpuses from different generators available for both, which saves us having to generate original content ourselves. So firstly, the Mario AI benchmark or framework, which is this lovely AI research tool that I'm imagine many of you are familiar with, that also comes pre-packaged with some pre-generated levels from different generative approaches, which is great for our purposes. And we also look at Boxoban, which is Google DeepMind's open source version of Soccerban, the classic block sliding game, also another sort of tile-based game. And these form our sort of domains that we looked at. Can we find visualizations of these generators? In terms of the behavioral characteristics we looked at, in this work, we looked at a very small set of very simple behavioral characteristics, all of which could be quickly calculated from the level representation itself. So it's normally an obvious point to improve on in future work, or to expand on, rather, to expand the number of characteristics we're looking at, and also expand the complexity, potentially extract some from simulated play. In terms of the visualization approaches we looked at, so we looked at 3 in total, 2 CNN-based and 1 benchmark. So we implemented VGG16, which is a kind of state-of-the-art convolutional neural network, which has been very performant at image classification. So we hoped it would perform well here because there's significant similarity between 2D levels and 2D images. But to benchmark, which we hope VGG16 will perform the best, but to benchmark its performance, we also implemented a much more computationally light, simple convolutional neural network. And also this technique we call vanilla dimensionality reduction, which I won't go into too much here. It's a technique that I talked about at the conference on games a couple of months ago. But basically, you apply dimensionality reduction directly to the levels themselves rather than to neural network embeddings. And it makes for quite a nice benchmark because it's much more computationally light. It's much more straightforward, but hopefully less performance than these more complicated neural network-based approaches. And just quickly on the design of the experiments, in each case, we held one behavioral characteristic back and trained the network on the other 3. And then we used that one that we'd held back to evaluate the final visualizations. So the correlations we were finding were with characteristics the underlying network had never seen. The idea being, if we found good correlations, this would kind of be an indication that we're finding some more abstract idea of like interesting diversity in that space and not just the very specific characteristics that we train the network on. So moving on to the results, starting with a big boring table of numbers. The sort of the high level takeaways for our results. In the Boxoban domain, the results were basically what we'd hoped for overall, with a couple of caveats. VGG16 performed fairly dominatingly, and significantly outperformed our 2 benchmarks and found fairly good correlations across the board, which is both good because it outperformed our benchmarks, but also it's a domain that we'd struggled to find good visualizations of in the past. So this was very promising in our eyes. On the much more negative side, in the Mario domain, there was no clear winner, and in fact, VGG16 significantly underperformed at finding robust visualizations, which is definitely something I'll talk about more in the next couple of slides, but certainly something to refine and investigate more in sort of future versions of this system. And relatedly, there was fairly high variance in the performance of the neural networks, which we're hoping indicates that like the approach might be sort of theoretically sound, and that these are kind of implementation issues. But again, that's something that needs investigating more. Just looking at sort of like the 2 most performant plots to give you kind of an idea of what the output looks like from this approach. As you can see, it's fairly similar to expressive range. You get these kind of 2D scatter plots of the levels. And we also visualize the most proximal, like the pair of levels that appear closest in the visualization, and the pair of levels that are most distant. And this is a kind of really rough heuristic, but we'd hope that if the technique is working well, the most proximal levels would appear very similar and the most distant levels would appear to be very different. And this is kind of like, I don't know, I think it throws up something sort of moderately interesting to me, where it kind of highlights the difficulty of like assessing diversity and the qualities of levels. Because even though the Boxoban domain was highly performant and the most proximal pair of levels are very similar in terms of these characteristics, they don't necessarily look supremely similar, and it's not obvious the experience of playing them would be similar either. So this is not necessarily a problem with the technique itself, but just sort of highlights the need for the right behavioral characteristics to find the correlation in. It needs to be stuff that's going to be immediately relevant to you as a designer in terms of the similarity and difference between the artifacts themselves. Cool, so getting close to being wrapped up here. So overall, we're sort of fairly happy with this approach and definitely going to explore it more. We think that sort of the benefits of it definitely make it worth further investigation, and there's a lot of general need, I think, in the PCG field for new and more robust heuristics and techniques for comparing different generators. Even though it's a very tricky area, there's a lot of value to be found there. I think one of the biggest conceptual weaknesses with this approach is that we were using an out-of-the-box neural network from the world of image recognition rather than something that spoke to games. So we'd like to explore something more bespoke in the future. And as I said, expand the volume and complexity of behavioral characteristics that we're looking at, as well as exploring like factors in domain performance. What games are easier to visualize and which ones are not. So that is it for me. Again, thank you all so much for your time and attention. If there are any questions now, I'd love to have them, but also please feel free to contact me afterwards if you have any thoughts on this work or in general on thoughts on how we can usefully compare generators. It's something I'm super interested in and would love anyone's thoughts. Thank you very much.